Example 4 involves quadratics in the denominator that have non-real roots. And these types are going to involve using an arctan antiderivative. I'll show you how to set this up in a second. So, if we take a look at this example here, the denominator is a quadratic. What we do first is we always check for factors to see if we can make it into type 1. So in this case, this is non-factorable. So the next thing that we're going to do is we want to test the discriminant to see if the discriminant is less than 0. If that's the case, it has non-real roots for that quadratic. And those types need to be done a certain way. So I'm going to test my discriminant in this case here. So I have 4x squared plus 4x plus 13. So I'm going to test my discriminant, b squared minus 4ac. B squared is 16 minus 4 times 1 times 13. And in this case here, we end up with 16 minus 52. I end up with negative. And because b squared minus 4ac is less than 0, this means we have non-real roots. If this is the case, this indicates what we call a type 3. And this will involve using an arctan form of this. Okay, so there's two parts to this. There's going to be a substitution part to this and an arctan part to this. Okay, so once we've established that, we need to set this up. Okay, and to set this up, the first thing that we're going to do is we're going to apply substitution. So the first step is apply substitution. Okay, so this is only if the denominator has non-real roots. We're going to try applying substitution. And to do this, we're going to let the u function be the denominator, x squared plus 4x plus 13. And what that's going to end up doing is we're going to generate a du, and the du is going to be 2x plus 4. So we're going to get a linear function for du. And what that means is that we want to have this 2x plus 4 as part of the numerator to be able to apply substitution. Now notice that this 2x plus 5 doesn't quite match. Okay, that plus 5 does not match plus 4. So we're going to have a leftover piece, which we're going to put into a different fraction. And that other fraction is going to be done using arctan, and I'll show you how that sets up. So the first thing is we apply substitution, and then we separate it out so that we can do the substitution in this integral. So we have 2x plus 4 over x squared plus 4x plus 13. Now, that is the substitution part. Okay, so one part is substitution. Another part is going to be an arctan part. So we're going to end up with an arctan part. So I'm going to do plus. And the way that the arctan part is generated is that there's going to be a leftover part for the plus 5 and plus 4 mismatch. There's going to be an extra plus 1. And that's going to be over the denominator. That's the same as here, x squared plus 4x plus 13. Okay, so this is the same as above. When we add this together, we're going to end up with our plus 5. But now what we have is a situation where we can apply substitution to the green part, and for the red part, we can apply arctan because we can make this a sum of squares. Okay, so this is our arctan part here, and you may not quite see it yet, but I'll show you the next step. So for the green part, we're going to apply the substitution. I'm going to do the integral. I'm going to replace the denominator with u, and the numerator, this part here, I forgot to put my dx in here, that numerator part is going to be the same as what I have here. So I can replace all that with du. So then my du goes into my expression. So that du is replacing that 2x plus 4 dx. And now I have an integral which I can do, which I applied substitution to, and I can undo that integral. And I have another leftover piece here. And this leftover piece can be done with arctan. And the reason is because now I can express this as a sum of squares. So I'm going to complete the square. So I'm going to end up with x squared plus 4x plus 4 bracket. And then I'm going to have, to make up the 13, I'm going to have plus 9. And that means I have a squared part plus a squared. So I have a squared and x squared part to this. Okay, so I'm going to apply my log to this one, log u, and this becomes plus the integral of 1 over x plus 2 squared, so there's my x squared, plus 3 squared. So now I can apply my arctan formula to this one. So there's my arctan. A squared is going to be 3 squared. X squared is going to be x plus 2 all squared. I'm going to plug that into the formula. So finishing it up here. The left part becomes log u. I'm going to replace the u with what I substituted u with, x squared plus 4x plus 13. There's a u part. Plus, now I can anti-differentiate the red part here. I have, it's going to be arctan, so using that formula, it becomes 1 over, this in red, it's going to be 1 over, in this case, a squared is going to be 3 squared, so a is 3, 1 over 3, arctan, and the x is going to be x plus 2 over 3, and then we can't forget the plus c. So I'm just going to shift this over a little bit so I can fit in my plus c. And then I have my plus c. Okay, so there it is. There's my derivative, sorry, my integral for 2x plus 5 over x squared plus 4x plus 13. And again, we need to recognize that this is a type 3 by first of all trying to factor the denominator. So that's the key. We try to factor the denominator. If it's not factorable, we check to see if the discriminant is less than 0. If that's the case, we can then apply the substitution to it. So we end up with a substitution expression here, and that du is really important. That 2x plus 4 replaces the 2x plus 5, and then we have that extra plus 1 left over, so we put that extra constant plus 1 in the arctan portion of this. So the green part ends up being done by substitution, the red part ends up being done with an inverse trig function, and we end up with our solution here. Now, a couple keys here. We want to make the du match the 2x plus 4, and it doesn't matter if we make it equal to 2x plus 4 or x plus 2 or even 6x plus 12, as long as those two terms, the 2 and the 4, are in the same ratio, we can take out the constant with the du to make them match the 2x plus 4. Okay, so as long as it's in that ratio of 2 to 1 for the coefficient on the x and the constant, we can account for the proportion. We can account for that, the extra proportion by dividing out that factor. Okay, so that can be incorporated with the du, which is perfectly okay, as long as we can end up with a 2x plus 4 to replace the 2x plus 4 in the substitution form.